Yes, I'll introduce you, Melissa, and then I'll leave you the space.
Sounds good. Oops. I have to remember that I'm actually live right now.
You are.
All right, we are live.
Wonderful. Okay, so while people are joining us, I will remind you of the events at the center this week and next week. Tomorrow we have the first meeting of the senior visiting seminar organized by the senior visiting fellow Nick Huggett, sorry, excuse me, Nick. And it starts tomorrow at 10:15 on Zoom, of course. It's Nick is going to be giving the first lecture of the seminar on cosmology beyond space-time. If you're interested in joining this seminar, you can go to the website and look at the calendar, and the link to register for the website is available there. Let me remind you, there is no talk on Friday because Pete is giving the Nicholas Fisher Medal for Systematic Philosophy to Thomas Nagel. The Nagel's lecture will be at 3 p.m. It's on moral realism and moral progress, so there will be no lunchtime talk that day. The next lunchtime talk is on Tuesday next week at noon, and it's going to be given by Nick Byrne, who is a postdoc at CMU and who will be next year an assistant professor at the Stevens Institute of Technology. And he will be talking about health and liberty. And you are all invited to join us for this talk. Today, it's my pleasure to introduce Melissa Jacquart, who is an assistant professor in the philosophy department at the University of Cincinnati, and she is also the associate director of the new, or at least relatively new, Center for Public Engagement with Science at Cincinnati, a wonderful new center for philosophy of science. And Melissa has got her PhD, obtained her PhD from Western, working on modeling. She works mostly on issues related to modeling and computer simulation with a focus on astrophysics. And she has published on these topics in a number of journals, including Philosophy of Science. And today, indeed, we're going to hear her talk about astrophysical computer simulations. And Melissa, so the floor is yours.
Right. Thanks for having me. So before I start to dig into the talk, I thought I'd start by giving a little context for the content that I'm going to be talking about, especially since these lunchtime lectures or talks can range from newly minted philosophical ideas to finished products, as was mentioned in the emails and on the website. So what I'm going to talk about today is kind of a mix of both of these. So some of the context might help with that. So as Eduardo mentioned, I do a lot of research on the work on models and computer simulations. And so I'm really interested in how these questions apply in the context of astrophysics. I'm interested in how scientists in this context construct their models and simulations, how they represent the world given their incomplete and partial representations. I'm also interested in when scientists say they've developed a good or successful model, what that means and how that's evaluated, as well as once you've done that sort of evaluation, how that justifies and informs claims about the real world. So that was a lot of what I was interested in grad school and underlying a lot of the work that I do now. Recently, as part of my first postdoc, I was at the University of Pennsylvania working as what I guess philosophers or science are now calling embedded philosophy. So I was and still am part of a research project in which I actually work with astrophysicists throughout all of the steps of their research project. And so this is a project related to dark matter and the use of models and computer simulations in that context. So I think part of you, or I can't really see who's in the audience, but part of you will be familiar with this project, but I'm going to talk a little bit about that as part of my talk today, this Observing the Invisible project. And so that's part of what my talk is going to be about. And so part of what I've been doing as that embedded philosopher is doing some of the science, but using that in some ways as a sandbox to explore philosophical ideas. So today's talk is going to be informed partly by using that as a sandbox for exploring philosophical ideas. And today I'm going to be specifically talking about idealizations. And this is largely inspired by the fact that I am now at the University of Cincinnati. I work very closely with Angela Potocznik, developing this Center for Public Engagement with Science. And when we're not talking about how philosophers can help or potentially help public engagement with science, we've been talking a little bit about the role of idealizations in science. And so my talk today is sort of a bridge of these two positions that I've had and where I am now. So part of what I'm going to be doing today is talking about this Observing the Invisible project, and then some new philosophical questions that I'm interested in the context of idealization and using that project as a backdrop. Okay, so as I said, the first part of my talk and an overview of what I'm going to be doing today is talking a little bit about this astrophysical program. I'll tell you a little bit about this project as a whole, how it connects to dark matter, and what we're doing with respect to computer simulations. I'm then going to focus on some of the philosophical questions that I'm interested in. And these are specifically, what role are idealizations playing in this project simulation process, and in offering explanations in the context of astrophysics based on these computer simulations. And then along the way, I'm going to try and highlight and discuss the kinds of roles and the kinds of idealizations that are at play, as well as try and argue for this being a case in which de-idealization plays a particularly important role. Okay, so that's my plan for today. So what I'm going to do now is sort of go back and zoom out to some of the big astrophysics questions that I'm interested in, and this sort of paint this picture of this sandbox that I'm really interested in, and this project that I've been working on as part of the Observing the Invisible project. Okay, so the current standard model in Big Bang cosmology is known as this lambda cold dark matter model, for those of you who aren't the philosophers of physics in this talk. And it's a specific parameterization of a set of mathematical equations from general relativity. This is the so this model and its parameterization is considered to be the current best model of large-scale structure formation in the universe, and is in agreement with astronomy's best observational evidence. Now, one of the most interesting things about this model is that all of the ordinary matter we can see, like stars, gas, you, me, this only accounts for 5% of the content of the universe. The rest of the content is these two sort of new entities. The first, accounting for 24% of the matter, is dark matter. It's a very mysterious kind of matter that we've only been able to infer its existence from its gravitational interaction with our visible baryonic matter, but we haven't directly detected any particle for it. It's a kind of matter we can't directly see, and so it gets this name dark. The second kind, accounting for the other 72%, is dark energy. So this is an energy field that we also can't directly detect, and it drives the expansion of the universe at an accelerated rate. And so because it's also dark in this capacity, it gets sort of this name dark energy. And so the project that I'm a part of is really interested in this 24% that's dark matter. So it's not visible, we can't see it, but nonetheless, astronomers think it's there. So why is that the case? So astronomy has essentially 5 main lines of evidence for this dark matter. The first, starting at sort of small scale and building up. So the first on the smallest scale comes from observations of individual galaxies, of individual disk galaxies and their rotation curves. It turns out there was this mass discrepancy between the mass that astronomers accounted for observationally and the mass that the theory said should be there. There needed to be much more mass than they saw, and so astronomers concluded there must be other matter on the edges of this galaxy. This must be some dark halo that all galaxies are embedded in. So this mass discrepancy is also present at larger scale structures, such as clusters of hundreds of galaxies that are bound together gravitationally. And so looking at even larger scale structures, by including dark matter into calculations, astronomers were able to get mass in the right distribution to either, say, hold the clusters together gravitationally or to see gravitational lensing that they saw in their observations. The fourth line of evidence on even larger scales still comes from large structure surveys and how those are formed through the merging of smaller scale structures. And again, this is a case where things just couldn't be held together gravitationally, at least according to general relativity, without this amount of visible matter also there, or about dark matter and visible matter also there. Okay, and then the last line of evidence is observed patterns that we see in the cosmic microwave background. Okay, so these are sort of the lines of evidence on the table, and what I want to do is go back and zoom down to this super smaller scale of evidence of a galaxy, a single galaxy's dark matter halo. So as I said, around every visible luminous galaxy is this halo of dark matter. However, unlike ordinary matter, we can't directly see or observe dark matter. We only detect it through these gravitational interactions. So one of the outstanding problems in modern day astrophysics, it turns out, is there's a mismatch between the dark matter mass accounted for observationally based on these luminous galaxies and the amount of dark matter that is predicted to exist by, say, that fourth line of evidence that I showed you, those really big, large scale computer simulations. Okay, so here's another instance of this. On the left is an example of what the computer simulations predict our local area in the universe to look like. Wherever you see a dot in there, that should be a galaxy with dark matter. On the right, however, is the galaxies we actually see based on our observations. And as you can see, there's a lot less of them. And so astrophysicists have so far only been able to account for a fraction of the dark matter that's supposed to exist in the universe. And so one of the biggest questions in astrophysics today is, okay, so where is all the rest of these predicted dark matter by these simulations? Where are all these, what astronomers call missing satellites? And so the group that I'm a part of, as part of this Observing the Invisible project, thinks we might have a possible answer to this. So first, I like to always show my research team. It's a really fun group. We're made up of both astronomers and of astronomers and philosophers. And like I said, this is sort of this embedded philosophy of science model where the philosophers are participating in the science, embedded in that capacity, along with the astronomers who are doing a lot of the work. So one of the crucial assumptions in this missing satellites problem is this coupling of dark matter to baryonic matter. So the working hypothesis in our group is what we're calling a dark galaxy hypothesis. While some of the missing satellites problems suggest that dark matter always couples with this luminous component, we're exploring the possibility that this might not be the case. Our working hypothesis is that at least some of the missing dark matter is in what we're calling dark galaxies. That is pure dark matter halos that have no visible baryonic matter, either because they lost it very early on or they never acquired it in the first place. Of course, a question like this is, okay, so how could such a dark galaxy be found, given that the assumption is dark matter is not directly observable, and we only observe it through its gravitational interactions with the baryonic matter when it's coupled to it? Our proposal is that some of these dark matter galaxies can still be found by these effects, and we're using dark matter's ability to interact with visible galaxies by gravity as sort of a marker or signature of these events. Okay. So this is an incredibly rich project. There's a ton going on in it. On the astronomy side, we're going to be doing some actual astrophysical observations. We develop computer simulations. A component of this project has relied heavily on citizen science. So that's been really interesting with various epistemic questions connected to that. And we're also exploring some public philosophy of doing philosophy of science and methods through films. But on the philosophical side, some of the questions that myself and my collaborator, Michael Weisberg, work on are questions like disunity of science, theory confirmation, questions about scientific realism. But the question I'm the most interested in is this inferential and explanatory power of computer simulations in this context. And so this is what I'm going to be focusing on in this talk, and some of the questions I've been starting to think about with that connected to idealizations. Now, before I get to the idealizations, I want to take a moment to highlight why I think getting a better understanding of how computer simulations are developed and how they gain their epistemic status is so important to this project. And I think this is due to one of the methodological challenges we're up against in astrophysics. So astrophysics, by its very nature, astronomers can't perform anything like experiments on the stars or the galaxies. There isn't anything to directly interact with. Astrophysicists can't create a real galaxy, see how it evolves over time. We can only observe what's already been happened. So it faces this observation-based epistemic challenge in that the subjects themselves cannot be manipulated experimentally. There's also this issue of sparseness of data in that we only have snapshots. And so astrophysicists get around this by bringing in computer simulations. Now, another challenge in astrophysics is that we're often developing models of systems that are aiming at modeling the entire universe or even a single galaxy. And both of those things are highly, highly complex. So astrophysical computer simulations in particular are in need of paying attention to considerations like approximations and idealizations. When are they warranted? How are they handled? How are they mediated? And how the simulations can then obtain their epistemic status and offer explanations about the real world systems. And so I think it's important to think specifically about if these idealizations are in our context doing what Angela Potocznik likes to say, running around rampant and unchecked. And so to examine these concerns, I want to compare part of this project to a recent account of idealizations and the aims of science offered by Potocznik in her recent book. So in her book, this is going to be an oversimplification of the book into a couple sentences, but in a nutshell, she starts by acknowledging that science is done by humans with limited cognitive capacities, and that science investigates a very complex system. And as a result of this, idealizations are widespread and sometimes, as she says, rampant and unchecked. But similarly, idealizations are incredibly useful to doing science because they help simplify the complexity that is inherent to the nature of science and the world. So in thinking about the story I'm about to tell you about my Observing the Invisible project that I'm a part of, I think there's going to be similarities to some of the points she makes in the book. And so I'm going to flag those now and return to them later. But the first is that science is best characterized as a search for causal patterns. Dependencies between factors are revealed under manipulation, and which causal patterns emerge in some ways depends on our representational choices. Scientists can also, or another part to this is that scientists rely on idealizations in order to detect these causal patterns. And that idealization's positive representational role is to indicate the nature of the factors' relevance to the focal causal patterns. So I think these parts to Patochnik's story are going to be present in what I'm going to talk about shortly, but I think there's going to be one important difference. So she thinks that idealization is inherent to scientific representation and explanations, but that we shouldn't really hold out hope for de-idealization doing much or anything to some extent, and that it doesn't happen as ideally or frequently as one might think. But I think this is going to be a case that's different from her account, in which de-idealization actually ends up playing a really important role in offering explanations and for astronomers drawing various conclusions. Okay, so that's a little bit about that as some backdrop. What I'm going to do now is move on to this astronomy project as a way to explore some of these ideas. Okay, so as I mentioned, astronomy is confined to snapshots. Here are what some of these snapshots look like. These are sort of pictures of what standard galaxies look like, spirals, elliptical galaxies. Here are some more snapshots, and these galaxy structures are what are called ring galaxies. Now, it turns out that galaxies of this shape are really rare. These shapes don't happen naturally in the same way ellipticals or spirals happen. These are what are called collisional ring galaxies, and they get their ring shape only when a galaxy undergoes a near head-on collision with another galaxy of just the right mass size. Astronomers have known about this for some time. In 1976, they started to use computer simulations as a tool to understand how these rings got their shape. And in these early simulations, the goal was simply to provide these general how possibly accounts for how these galaxies get their ring shape. They chose masses for the two galaxies, as well as angles for collisions. And they varied them as a means to explore how they might interact and determine how these collisions could occur. But there wasn't really any need to capture the trajectory of every particle. They were just using this as a way to explore these how possibly accounts. And so here's another view at what these look like, varying how many, varying just different parameters, different setups, different conditions. Now, simulations have obviously developed a lot since 1976. Here is a more recent one, and this will give you a better sense of what I mean when I say these are collisional ring galaxies. So this is going to be a collision between an elliptical and a spiral galaxy to form a ring galaxy. So the image in the corner on the left is a snapshot, an actual observation. And what's here is a simulation of that image based on what astronomers were able to obtain in terms of observational evidence and data. So I'll play that for you. Galaxy rotating. Here comes in its companion. It collides with it, and it creates this ring shape that looks pretty close to the image in the picture. But after a few rotations, it dissipates, it dissolves away. Okay. So here are two more actual ring galaxies. These two happen to be almost identical in structure. So most of these ring galaxies have a clear companion, another galaxy that collided with it and created the ring. On the right is ARP 147 and its companion. However, in looking through catalogs of peculiar galaxies, there are a handful of these ring galaxies that have no clear companion. On the left is 2 Zwicky 28, and this is a ring galaxy that has no companion. You might think it's some of those other objects in there, but they're not. They're all far, far, far behind it and are not its companion. So given the current explanation is that the only way these ring galaxies can obtain these shapes is through undergoing a collision with another galaxy, our team is exploring the hypothesis that 2 Zwicky 28 had a collision, but that collision happened to be with one of these pure dark matter halos, and it's why we can't see the collisional companion. So our goal is by obtaining observations and trying to simulate a variety of ring galaxy collisions, we'll be able to say if this ring has the right signatures for a collision and perhaps predict where the dark matter galaxy collider is in that image. Okay. So if this is all, though, that we have access to, these snapshots, where do astronomers go from here? Well, as I said, we start by learning about these cases where we can see two observable galaxies interact. These are called luminous-luminous collisions. We've looked through a handful of catalogs and observations to get a sense for what these look like. We've taken observations of these these instances and gotten a sense for what these collision looks like when you can see both galaxies. And this is just one example. This is an observation, our data, and then a simulation of what this collision might actually look like. Okay, so from this, we've identified a set of key defining properties that these rings seem to have that is in agreement with other observations. They're always defined in a very specific way. They have these narrow rings. They always have this very blue, like literally the color blue, young stellar population. They're all rotating in a specific way. They're all expanding in a specific way. They have these other characteristics that are always present. And so what we've been doing is using these as a guide for the construction and evaluation of dark matter, luminous matter collisions, and also in terms of looking for other potential ring galaxies. So we have a handful of candidates right now, but this 2Zwicky-28 is our most promising one. So one of the things that we've done is we've gone to some telescopes in Chile back when we could all travel and gotten some observations of this ring galaxy as well as some others. And these observations are guiding the information about the kinematics in this system. And so we build out these data cubes to get a sense for what these ring galaxy actually look like and what's in them. Okay, so that's the observation side of things. And then there's also this simulation side of things. So I want to say a little bit more about that right now too. So for our simulations, we're using this code called Gizmo. This code houses a bunch of background theory and knowledge. This includes components of the universe, such as which we're taking to be a lambda cold dark matter understanding of the universe. It allows for flexibility in terms of inputs. It has the laws of physics, namely gravity, as driving structure formation. But most importantly, and in contrast with some of the previous astrophysical simulations, Gizmo is one of the first codes to really prioritize fluid dynamics and star formation and feedback as a critical part of its simulations. All prior astrophysical simulations have left out those features, but these features are essential when you're considering individual galaxies, single galaxies, how those develop over time. You need stellar feedback in there. Okay, so by including feedback in these realistic environments, simulators hope to be able to increase the predictive power of galaxy formation simulations without any of this fine-tuning of actual galaxy formation models. And so part of the slogan for these simulators is don't trust models that don't do star or interstellar medium right, because interstellar medium and star formation are such critical drivers to single galaxy evolution. And so our team's motivation for using this Gizmo code is that it also has this capacity to model single galaxies really well, but also includes some more fine-grained control over parameters that may influence the evolution of single galaxies. For example, we can turn on and off different properties in the system, some of them even that would modify what kind of dark matter is used in the simulation too. I'll talk a little bit more about this at the end, because Gizmo's ability to do some of this idealization is also why we think it's a better choice. Okay, so the first task in developing these simulations is to get a bunch of data. In constructing these, we have a number of parameterizations that need to be set in the simulation, and all of these on this list are based on observational data we have from real galaxies. And once we build those, we get to do the fun part, which is actually smash things into each other. And so this is just one of our simulations of a pure dark matter galaxy colliding with a luminous galaxy. So on the left is the gas and on the right is the stars. And so this will start rotating, and then we will, this is right before a collision with a dark matter halo. it hits with the dark matter halo, and we see a ring galaxy forming in both the gas and the stars. And then it dissipates over time. Okay. Here it is from some other angles at the start, evolved disk, and after the pass. This is a list of all the ways in which we're changing the parameters in our simulation and exploring what impact these have on the collision. And here's just one example of this parameterization changing. We're changing the halo concentration class, how concentrated the halo is. The more higher the concentration class, the stronger effect we see. We can also develop computer simulations that show us the velocity field, so how the galaxy is rotating and expanding. And then once we've done all that, sort of our next comparison is to go back and incorporate the actual evidence we have for our specific galaxy and see what that shows us. Namely, to see if our velocity fields in the simulation match the observation, and use that as a point for talking about where that dark matter companion could hypothetically be. Okay, so that's the simulation side of things. What I want to do now is return to the questions that I raised at the start of this talk. And these are namely, what role does idealization play in this project simulation process and in offering explanations about our phenomena? Namely, how did these isolated ring galaxies get their shape? And so I want to try and answer this question by breaking it up into maybe 3 different parts. And so what I want to do is return to the comparison, or return first to the comparison I suggested at the start of the talk with Angela Potocznik's work, and then a connection between idealizations and the aims of science and what those aims look like in the context of astrophysics. I then want to highlight the kinds of idealizations that are being deployed in developing these simulations. And then through examining what kinds of idealizations are being made, I want to argue for the importance of de-idealization as a part of providing explanations in our case. Okay, so that's my plan for the rest of this talk. Okay, so first returning to what I guess I'm going to call idealizations and the aims of astrophysics. Potocznik, remember, claims that science is best characterized as the search for causal patterns, that is, dependencies between factors which are revealed to some extent under manipulation. Which causal patterns emerge depends on our representational choices. And she thinks that scientists rely on these idealizations in order to detect these causal patterns. And that idealization's positive representational role is to indicate the nature of factors that have this relevance for these focal causal patterns. Okay. So I think we see these dimensions present in the case study that I've just detailed. The initial idealizations from, say, the 1976 simulations identified some of these causal patterns, but over time, these causal patterns were made better and understood through this process of developing more and detailed simulations, but at the same time only revealed because some things had been had these idealizations also in play. So in thinking about our target system, the structure of a single galaxy is highly complex. They contain stars, they contain stellar remnants, it's interstellar gas, there's dust, there's also this dark matter. But even these very simple simulations where we've idealized it to even say just mass and point particles, astronomers had identified the causal patterns of the ring galaxies. And even with radical idealizations like that, they were able to capture the relevant causal dependencies. So I think so far the role of idealization in this context and the aims in deploying idealizations is telling a similar story to the one that Potocznik tells. Okay. So the next point has to do with thinking about the kinds of idealizations at play in astrophysics. So I'm going to be following some of Michael Weisberg's discussion in particular here, but I want to consider three possible kinds of idealizations that our astronomy project might be deploying. So I've considered some of the aims, why we're idealizing. Now I want to look at how that's happening and the kinds of idealizations that are happening. And so some of the literature flags this into or at least three different instances: Galilean idealizations, multiple model idealizations, and minimalist model idealizations, or minimalist idealizations. So I think we can first see that this project is deploying these sort of Galilean idealizations in that it's introducing distortions with the goal of simplifying in order to make the models and simulations computationally tractable. We see this in that we're trying to model highly complex systems of, say, a galaxy, and we see this with literally the computational processes as they develop as well. So obviously in our 1976 models, it was super pared down so that it could actually run, and that's part of why they had those idealizations. And even in the case of our gizmo codes, we have a limit in terms of how many particles we can handle. We can handle more than the point particles of 1976, but there's still an upper limit at which point the system crashes. And so in both of these instances, this seems like instances of this Galilean idealizations. I think this case is also deploying the strategy of multiple model idealizations, in that there are several distinct simplifying models are being employed together to shed light on a phenomena, namely ring galaxies. So we see this in comparing simulations as they progress over time, meaning the 1976 simulations compared to contemporary models and sort of all the models that were made in between. So in moving from the point particle simulations to the more complex but still idealized simulations, we now include feedback and fluid dynamics. The simulations are still testing these hypotheses related to if the rings are obtaining their shape through these collisions, and if this cause is competent to sort of produce this output. And it's through these different idealizing assumptions about the basic physical processes involved in the ring galaxy formation that we're determining under what conditions these ring galaxies form. We also see this if we look at just the gizmo simulations, the ones that we're deploying right now. So as I mentioned, a step in this process is changing the parameters in our simulation and exploring what impact these have on the collision. And I think this should be thought of this kind of multiple models idealization under what condition the ring galaxies form, but under more important conditions under when they don't form. And it's this multiple models instances of idealization that allows us to constrain our possibility space in this respect. Okay, and then finally, I think this is also some instances of minimalist idealization strategy. And this is the strategy of introducing idealizations to eliminate all but the most significant causal influences which give rise to the phenomena. So the earliest ring galaxy models demonstrated this strategy of minimalist idealizations the clearest. They included only the factors that made the relevant differences to the occurrence of the character in the phenomena that was in question, and this namely being the mass ratios, the angle of the collisions, at least in our case of the ring galaxies. And then also later models extended this by exploring if there are any other causal influences that could give rise to the phenomena. Now, this actually leads me to the third point of interest that I'm interested in this. And this is connected to de-idealization. So in a recent paper by Nutila and Morgan, they're examining the role of de-idealizations in science. They suggest that the implicit view in the idealizations literature is that idealizations involve some kind of reversal or reversible process. However, they want to argue that de-idealization isn't necessarily just this simple reversal thing that happens. And in fact, they offer a menu of other kinds of processes for de-idealization. And they think when you actually start to pay attention to what's going on with these de-idealizations, there's a whole bunch of really interesting and overlooked things that we might be able to learn. So they see de-idealization as or different sort of de-idealization strategies or options on the menu as recompositing. So this is reconfiguration of the parts of the model with respect to the causal structure of the world. Reformulating and concretizing, which is dealing with issues of representing in focusing on two different sides of the abstractness of models, either they're symbolic or computational formation, and then situation, which addresses the applicability of models to particular situations. And it's concerned with not just how a model can be de-idealized to represent some determinable target situations, but how such a process enhances their uses in theorizing. So they've been mostly looking at models in econ, but I'm really interested in thinking about if there's a way to extend this framework for useful thinking about de-idealization that's happening in the development of these astrophysical models. And so I think if we take seriously their suggestions and thinking about de-idealization in this more complex matter, we see that the use of the simulation codes in these contexts that I'm studying that are flexible enough to de-idealize representations plays a specific role in reasoning about the results from these simulations, and that it's de-idealization where some of this argumentative power in this reasoning process lies, in using simulations to connect a vast array of these different astronomical observations or phenomena to arguments that might be embedded in the simulations themselves. Okay, so let me say just a little bit more about this idea. So in thinking back to what we're doing in our project, part of what is going on part of what we're doing by deploying the gizmo simulations to explore the formation of ring galaxies is adding back in features of the target system to the simulations that in some ways had been originally de-idealized away and might actually be difference making. In our gizmo simulations, we've learned about various structures through a de-idealization process. And namely, in this context, part of what we're de-idealizing is how stellar feedback operates. And as mentioned, part of our code de-idealizes this on the scale of individual galaxies. That's super important because it's critical to how those galaxies develop and evolve over time. So in the process of fleshing out some of these minimal causal models with these more concrete details and starting to include stellar feedback, we started to get systems, for example, that had more features that were present in observations. A good example of this is spoke structures. So this is in my bottom right-hand corner image. It's these lines in between the outer ring and the center. Once you start to add stellar feedback, you actually get those in your simulation more prevalently than in the past, and are a crucial aspect to these objects. Okay, so that's part of it. And it turns out the spoke structure emerges in the simulations once you have this complex structure, and we're able to gain also some temporal information from these spoke structures too that we didn't have before, namely they only occur at certain temporal instances in the evolution of the system. Okay, so that's looking at looking at some of this in the context of just the Observing the Invisible Ring Galaxy project specifically, but connecting this to the use of simulations in astrophysics more generally, a point that the authors that Nutila and Morgan make in their paper is that idealized models embed a scientist's theoretical or conceptual commitments about either the system or elements of the system. And part of what we're doing in this de-idealization process is thinking about how conceptual elements can be de-idealized in different ways for different sites and for different purposes. So to just think of how this plays out in the story of computer simulation code in astrophysics, namely a group of simulators will develop a code. There will be different research groups that put that code to different purposes. Our group is just one, but other groups use the exact same code for different purposes. And so in this process, each group is in some ways de-idealizing parts of the code for their context and given their goals. And with the different research groups doing it, it's offering this plurality of tests of that simulation code. If it works out well for most of the groups, it adds some power to the simulation code. It connects all the different research groups' independent observations to some of the more global arguments embedded in the code. But on the flip side, if it breaks down, if it fails to work in some of these processes through this de-idealization, it allows for, or perhaps highlights, instances in which the code's is not overtly flexible. So this is something that in astrophysics, codes get accused or can be accused of sometimes being overly flexible, being able to accommodate too much data. And if they work in all cases, we should be worried about that too. So codes breaking down through this de-idealization process is also interesting in terms of adding to this fuller understanding of what might be embedded in these models or simulations. Again, connecting this back to some of the bigger picture arguments in astrophysics, this is also where there's this place to connect it to, you know, some of the justification for dark matter, dark energy, perhaps. And so that might also be adding some of the emphasis here. Okay, so let me just try to tie some of this all together. So I was interested in thinking about the ways in which idealizations are at play in astrophysics. I'm using my project in some ways as a sandbox for exploring some of these ideas. Namely, these ideas were what are the aims of idealizations in our context? Why are idealizations being deployed? What kinds of idealizations and idealization strategies are present in these instances in astrophysics? And in this context, the capacity to de-idealize models and simulations seems to be particularly important to the ultimate goals that astrophysicists have in mind. So first, with respect to the aims of idealization in this context, a lot of what I think Potočnik says rings true. Causal patterns emerge, and it depends on these representational choices, which are facilitated through these kinds of idealizations. Some of the features emerge because of these representational choices, and our choice to include more features in the simulation than were there originally, namely de-idealizing is part of that story. But there also needs to be a process-based evolution of the models too. We start out with sort of like our idealized minimal model that over time has undergone de-idealization, and by adding back in those features, they either may or may not become relevant to producing these overall phenomena. And astronomers are doing this process in order to get a closer, richer understanding of what's actually in these systems. And I think when you have that process, it strengthens this sort of the explanations for these cases. And it's in these cases that there's this need to capture some of these causal aspects to what's going on. So I see some of these present in our cases. Something I really want to explore is if this isn't present in most cases, how this connects up with some of the larger scale simulations as well. That's something I want to spend some more time on, but I haven't quite yet. And then I think that the simulations are being developed in order to account for more of these observational features of these real world systems. And as more features to the target system are added back in, namely once we have better understanding of what's actually in the target system in astrophysics, like dark matter and dark energy, like I said at the start, we don't really have much of a sense for that, but nonetheless, it's a huge component. Those will be instances of de-idealizing again these models and making it more complex, and hopefully the accuracy and details of these simulations will be improving as well. But again, I think that some of the richness that's coming in the context of astrophysics is through this process, not of, yes, in some ways of idealizing things such that we can get a bare understanding of what's going on in the universe, but we're with more computational power, we're able to de-idealize. And that's where some of the really interesting justification for claims in astrophysics is coming now. All right, that's my talk.
All right, thank you very much for this talk. So with webinar, we can clap, but I'm sure the heart is there. Let me remind you how we're going to be processing. If you have a question for our speaker, please go to the bottom of your screen and click on the Q&A button and just write your name. And I will promote you to the status of panelists, and then you can ask your question to Melissa directly instead of having to write your question in the Q&A. So please go there now and just write your name in the Q&A button, and I'll promote you to the panelist status. All right, so while people are doing that, okay, well, here's already someone. All right. All right, Mike, the floor is yours.
I can't start my video, but hi, Melissa. This was
you, Mike, so it's fine.
Okay. I guess I have a question about how you're seeing the claim that part of the progress that's happening is in the de-idealization. And I guess this is a question about whether there are any checks on the de-idealizing process, which we can sort of construe as itself an idealization of sorts. So one thing that you might be worried about, especially when you start trying to move between this different scales, like to get up to the large scale structure, is that by the time you've de-idealized each individual system, they're not going to be particularly normally distributed around the paradigmatic galaxy structure. And yet it's the sort of paradigmatic one that is important in the between scales picture. And so I guess, do you see this as a part of the narrative to tell where you need to be careful that in the process of de-idealizing, you're sort of maintaining a regression to the mean of some sorts, or is it all up for grabs?
Yeah, that's a good question. So, I mean, I think one of the reasons I like, especially how, I think I'm not saying their names correctly, but Nutila and Morgan talk about this, is they like the de-idealization stuff because it helps draw more attention to some of that sort of like middle stuff that's going on to some extent. So and I think this is especially interesting in the context of astrophysics and the large scale simulations, because so much of the simulations at any scale is driven by theory. And what de-idealization starts to draw attention. I'm getting feedback on my end. I don't know if, but so what that starts to draw attention to is where some of that scale relevant stuff really depends. So in thinking of your question of like through this de-idealization process, how do we have these sort of checks and balances at the appropriate scales, at the appropriate levels, especially if like I mean, in some ways, I think this is just like another level at which we need to pay attention to where astrophysicists are entering into when they do de-idealization. Is it in terms of like adding the features back in? Is it adding that sort of like contextualization and making it concrete with the data? Again, that's one of the ways in which you can de-idealize that, that they draw attention to in their paper on de-idealization. But there are other ways in which that can happen too, when you're paying attention more to de-idealization as it relates to, you know, actual representation in the process. And so I guess it's what I think is nice about focusing on de-idealization in this is it draws attention to trying to unpack, you know, those decision points when you're adding things back in that capacity. And so in thinking about especially sort of like moving from small scale to larger scale stuff, I think that that's where, you know, returning to, okay, so originally this was, you know, just sort of idealized in this capacity. We're going to, you know, unpack that for moving up a scale. I think that that's going to force us to think through some of those decisions in a much more rigorous way if perhaps we're highlighting the narrative of de-idealization in the process and acknowledging that that's what's going on, as well as, you know, just acquiring more data to sort of fine tune things. So I guess that's sort of a whole host of things that kind of answer your question.
Mike,
What?
you want to follow up, Mike? We got a bit of time. So.
Yeah, just that was helpful. And so I guess let me try saying a view back to you, and let me know if this is on track for how you're thinking about it. The activity of de-idealizing, say with regards to a collection of galaxies of interest, is to not de-idealize the subject matter of galaxy, but to move away from the subject matter of galaxy in favor of this particular galaxy or that particular galaxy. And of course, that's going to create concerns in our between scale story when we want to move from one level up to another. But that's somehow, that's good practice, or it's good that we should be attending to the difference between the subject of galaxy and each particular one in the set. Is that?
I think it's a yes. And I think part of what you can do in sort of those like localized, you know, instances, say I'm down here looking at individual galaxies and you all are up here looking at like large scale stuff, is if something in sort of like this de-idealization process helps raise attention to something being super relevant. I mean, stellar feedback is one of the things that sort of like the small scale folks are trying to like yell up to the large scale folks, like, this is a really important feature of how our systems are evolving. And if we start to add those back in and we start to get dramatically different results, that might inform just how seriously you need to be assessing or reevaluating the idealizations that are present at the large scale, in terms of if those idealizations are justifiable, or if, you know, computational tractability permitting, that needs to be added back in to some extent and contextualized. Yeah.
Great. Thank you.
Thank you, Mike. Chris, the screen is yours. Melissa, could you turn the presentation off so that we can move beyond the...
Hi, yes, can you hear me?
Yeah, we can hear you, Chris, thanks.
Okay, great. Yeah, for some reason my video was unable to, anyways. Great, thank you so much for the talk. I enjoyed it. I do have sort of like a question about, a worry about the methodology and the general approach. And it's sort of like a, wait a minute, not so fast kind of question. And I don't know if it's gonna hook up, you know, too substantively with what you had to say about idealization and de-idealization, but I don't know, maybe there's some connection. You can help me out with that if there is. But so, you know, what is a dark galaxy? So my worry is about appropriating dark galaxies and the dark galaxy hypothesis as the kind of hypothesis that's in the business for doing the kind of explaining and uncovering of the causal patterns of the world, as you put it. You might have the following conception of scientific explanation. I mean, you might think that scientific explanation is in the business of removing in a factive manner puzzlement, right, about particular phenomena, about particular occurrences. And there seems to me to be something suspect about looking to an exponens about which we don't know hardly anything in order to use that exponens, potential exponens, to remove puzzlement about something about which we're puzzled. And so, look, we don't really know what dark galaxies are. There's no consensus that we've detected them. Dragonfly 44 set aside. I mean, it looks as if the dark galaxy hypothesis might even be incompatible with particular conceptions of dark matter. So, for example, if you thought of dark matter as baryonic matter, if you thought of dark matter as as a brown dwarf, I mean, these look like, at particular massive scales, they look like stars. But dark galaxies are the kinds of things that aren't supposed to have stars. Moreover, brown dwarfs do emit electromagnetic radiation. It's just hard to detect them, but they're sort of like not in principle undetectable. So, there's something odd, it seems to me, about looking to this kind of hypothesis about these kinds of unknown systems or things to explain and reveal the causal structure of the world. And so, if I'm right in being suspicious on this point, one wonders whether there are any lessons to learn about simulations and idealization and de-idealization and the like. Sorry, that was long.
No, that was good. I mean, in some ways, this question pushes me on a lot of the things that right now I'm like deeply thinking about and just like not sure where to go with, because I mean, like in some sense, at the end of the day, for a lot of the things that I'm interested in, I seem to keep running into this wall of needing to deal with scientific explanation, or realism. At sort of like the fundamental juncture point in terms of like, okay, but if you want to then make those claims between the simulations and the real world, there's going to be some sort of like underlying ontological commitments that maybe I'm making or not making to sort of allow me to make that move. But I mean, I think the really hard thing about some of this is exploring those different options in terms of possibilities, in terms of what the explanation could be. So one of the things that we really like about this ring galaxy case is, a lot of the other dark matter cases that I talked about are it's always gravitational interaction. It's always adding things in to be able to, account for it. And so there's something that people feel, and I'm working to try and identify what about this case makes people feel this way. But, the fact that these are actual rings that are being interacted with something, and it's in a way a different visual kind of interaction than just things being gravitationally bound together. This is like, I don't know, something more than the other cases that, if there isn't a companion there, you have to explore what the other possibilities are. And some of that, I think what is interesting is, forcing astrophysicists to question some of these other fundamental assumptions they have, like the fact that baryonic matter always partners with or couples with dark matter, that they're always there together. And so in some ways that pushes that into a different space of consideration. But it's these puzzles that make you say, okay, so if it's not that, what else is our explanation for these kinds of things? Something has to go back to the drawing board. But in terms of connecting that back to some of the stuff on scientific explanation, is it just a matter of like moving the puzzlement? I mean, this is partly why I'm interested in computer simulations in the context of astrophysics, is because there is literally no other way. And so if we don't have computer simulations in this context, and we don't use models in computer simulations, I mean, maybe we need to sort of do the same thing with the ring galaxies, like go back to the drawing board and thinking about how we reason about these. But this is the only in-path that we have to exploring some of these systems beyond observations, given the challenges that the science has. So I don't know if that's like quite a satisfactory answer. I mean, this is part of what I'm trying to figure out is, you know, at the end of the day, this is going to be a matter of giving various explanations to this. And are these debates making similar moves, or are they making different moves? That's what I'm really interested in.
Awesome, great, thank you. Yeah, it looks like we're both worried about the same sorts of things. Yeah, good, okay.
Thank you, Chris, and sorry for the camera. It might be the setting of the Zoom webinar that needs to be changed. I apologize for that. Sharon, the floor is yours.
Hi, thank you, Melissa. That was really interesting. I have a clarification question. So somehow when you were explaining how this worked, I was thinking of the code as being a matter of interpretation and less a matter of de-idealization, and the model, and then there seemed to be a second thing, which was the de-idealization of the model. Now, I think maybe I can figure out how those go together, but I was hoping that maybe you could clarify that for me.
Yeah. So this is something in reading the paper that I mentioned, I'm trying to think through, and I don't know yet if it's going to be helpful to put them into the nice little boxes that they have of menus. But I mean, so part of what's going on in these astrophysics cases is some of it is a matter of, I guess what in astrophysics is just like parameterization and adding in values for various parameters. And trying to, in some ways, de-idealize by adding actual data in. So in some ways, like, again, I'm thinking of the codes that I use. We're able to download this code package. It's in sort of an abstract sense, this kind of nice little code formula where we can add in various parameters. And in some ways, that's a way in which we can de-idealize by giving specific contexts and comparing those contexts to other contexts. And so there's an aspect of sort of this like contextualization or concretization, I get tongue-tied with that word, with respect to de-idealizing in that capacity. And then there's also sort of this situation of putting it in various contexts, in thinking about it with respect to some of the theories. I don't know if they necessarily talk about it as interpretation, but I mean, part of what's behind a lot of this is representational choices. And so when you said code as interpretation, I think that might be the closest that it is in this context. Is that helpful, or is there somewhere else that I can say a little bit more?
No, that's good. That's kind of what I was thinking. I just wanted to make sure I was understanding that correctly. Thanks.
Thank you, Sharon. There's no one else right now in the Q&A line. If one of you has a question, please write down your name in the Q&A box at the bottom of your screen. I'll promote you to the status of panelist. Meanwhile, I can ask a general question, and you know, it's basically what I wanted to know is whether you agree first that there are cases where somehow the idealization just doesn't matter, and if so, what's the contrast? What are the principles that tell us, oh, in that case, not simply in that case people are de-idealizing, but in that case people should be de-idealizing. In that case, people actually need not de-idealize. So what are the principles, normative principles that should in a sense guide our scientific practices?
Yeah. So in terms of, I mean, I think one of the things that sort of drives instances of de-idealization in these contexts is sort of like the purpose that the model or the simulation is put to. And so I think that this is perhaps something that isn't perhaps emphasized enough as part of these processes, but I think depending on what purpose you put it to, a lot, like some of these kinds of idealizations that I've been talking about really don't matter. I mean, especially whatever the research question is at hand, some of these things might not be relevant. So again, thinking sort of like early on in the history of the astrophysics simulations, like they really did just like want to have a better general understanding of what was going on. And so they really didn't need to de-idealize much very quickly. I mean, they were still able to get some kind of understanding of what was going on. They were still able to get like a description of what was going on. In some sense, they were still able to offer predictions about what was going on in these systems. And that seems to be a lot of what they were really interested in. But when they started to think about, in some ways, extending like what their model or what their simulation was being put to, what the purpose was, what the question of interest was, that seems to be the place where some of these de-idealizations come in and need to be more relevant or more salient. I mean, and some of this I think is tied to them ultimately wanting instances of these explanations. So to some extent, these cases where de-idealizing doesn't really matter is if you feel happy enough with the description that you're getting, or like satisfied enough with the predictions that you're getting, if they're proving to be adequate enough for your context, then it seems like these are cases where de-idealizing in these capacities don't matter. And in some ways, maybe they add a little oomph or like reason for you to think that the predictions are even better because they've added in these extra things. But I think that that's not necessarily tied to having a good prediction, but offering a good explanation for why that's a good prediction. And so I think whenever there's, I mean, this is sort of like the question I keep coming back to, whenever you're pushing up against some of these issues of offering explanations, it seems like adding in more of these capacities seems to play a larger role than when the purpose is just sort of offering these predictions or descriptions in some contexts.
All right, thank you very much. John, the floor is yours.
Hi, Melissa, can you hear me?
Yes.
Yeah, I just say, Edouard, that the screen says that the operators have blocked us from turning on our video, so that is the problem. In my case, this is no great loss. You don't get to see me.
It's always a loss not to see you, John.
Melissa, that was terrific. That's enormously exciting. I have to say, I'm really just energized by the thought of the overall science that's being done here. I mean, the idea that one can detect non-luminous dark matter galaxies by this ring interaction is just extraordinary and wonderful. I kept wondering why a galaxy that big can't be detected by gravitational lensing, but that's not the question I wanted to ask. I wanted to think about the philosophical issues here. So for us, we want to try and figure out what modes of argumentation are being used, what foundational interest is going on here. I think you've identified the big thing, and that is that these simulations are all about idealizations. How much do you de-idealize? What do you get away with? What can you get away with? What happens when you don't? But there's a second form of argumentation that's being buried that I think is worth thinking about. I think the best way to describe it is it's a surrogacy inference, right? So think about the simulation of the ring formed by the collision of a luminous galaxy with a dark galaxy, right? So what you did was you showed us the picture of it was actually seen of a ring galaxy with no obvious companion luminous galaxy. And then you showed us a simulation of something else, right? Now, idealizations are normally to matters of general principle. There was no general principle here. It was quite a specific collection of luminous bodies and dark bodies, and they behaved in a particular way. And then the inference that was being made was, now we understand what's happening in the luminous case. Now, there's a lot of idealization going on here, but there's one extra thing going on, and that is that you can have a very specific surrogate for the process of interest. So the question then becomes, how are we to think about that form of argumentation? I don't know how much literature is out there. I think the closest literature is the analogy literature, but the analogy literature is a little bit too weak because the link between the simulated surrogate system and the system of interest is a great deal stronger than what normally happens in analogical inference. But I think the template of analogical inference is maybe the right one. There's this idea that's what's happening generically in that one simulated case. What's happening in that one simulated case is somehow generic behavior in some range of variation. Anyway, it's just a thought. I don't know if anyone's thought about that. I don't work on simulations, so I'm guessing this is probably out there somewhere.
No, but I really like that. I mean, I hadn't really thought of it in the context of thinking of it in sort of like the surrogacy aspect, but also, I mean, this would, you are the right person to pose this question in some ways back to, because in some ways that is just like a different form of a kind of inference that you're making, or at least a step in the process. But yeah, I guess analogy probably is the closest thing, but I don't know if there's anything in simulation literature that talks about, various simulations acting as sort of like the surrogacy, because there is something about the surrogacy that is a little more at least connected to some of the data and isn't quite an analogy in the exact same capacity, but
yeah. Like there's a literature to be written.
Yeah.
There's a hole to fill in the literature, someone should do it.
Thanks, John.
Thank you, John. Hélène, the floor is yours, and I believe now you can turn your camera on. Indeed.
Hey, Melissa, thanks for the talk. My question is a follow-up on the other questions about de-idealization. So I'm wondering, to me, it seems like there's two separate targets for the de-idealization process. There's the code itself, and so what you described with including feedback, et cetera, might be like an example of de-idealizing the code. But then along the lines of Mike's question, like the individual galaxies seem like you're de-idealizing by using these aspects of the code that you now have available. So the question I wanted to ask you is, do you think that there are separate processes for checking these de-idealizations? Because it seems like the code de-idealization just happens on a different scale, but not like, yeah. So I don't know if you think that there's checks to do that are separate in the general case as opposed to the particular galaxy's case.
That's a good question, Helen. I mean, this was something, again, like in some ways, this is, I think, my second attempt at thinking through some of these ideas in a more concrete way. And this time when I was thinking through, I was thinking actually a lot of some of your work and some of Marie's work. I'm going to say Marie's last name wrong too, because I'm just bad at saying people's names. But her work on robustness too, because in some ways I've been trying to figure out, like, is de-idealization, or what might be different about de-idealization from, say, just doing like straight up robustness analysis, because I think that sort of targets the second aspect to the question that you're asking there, in terms of like, when you're working on just galaxies or like working within a context versus when your target is the actual code itself. Part of what the simulators do is just this intense robustness analysis, which is in some ways, tweaking parameters here and there, changing different aspects, but in some ways that is informed by wanting to do some of this de-idealization stuff. So I mean, I think this is also what might be interesting here too, in terms of like paying attention to the de-idealizations, but I mean, again, especially thinking of the question you're actually interested in, like, how do you keep these checks and balances? Because like that's part of why we have de-idealizations. It's also the danger of de-idealizing. But yeah, I mean, it's I don't know. I think I need to think more about it. But part of me wonders if robustness analysis might be playing a part in the story, just because that's a way to do these checks and balances. And is also a way to attend to de-idealizing and idealizing at the same time. But I don't know. I'm thinking more about that. I don't know if that's helpful, or if you want to press me to try to think more out loud about something else. But
no, that's good. I'm just thinking of cases where individual galaxies teach us things about the code generally and how to think about the de-idealization happening there.
Yeah. Okay. So I said a little bit about like the larger scale, like when you're looking at just the code, but I mean, again, this is like one of my favorite examples from working with the astronomers themselves and these ring galaxies is this weird like spoke structure that they have that, you know, really doesn't start to emerge until you do some of this de-idealizing, until you add back things about stellar feedback. And again, if you're looking at some of like the stuff that like the FIRE group out at Caltech and them are doing, is trying to do some of that really important de-idealizing so that we have a better understanding of what happens when you sort of like evolve a single galaxy over time. I'm trying to think through some of the ways that they've done their testing. I mean, a lot of how it has been is, again, just situating it with the data. So they test their code by saying, okay, here's what we know about our own Milky Way. Can we reproduce that exact same galaxy, and how close do we get? Can we do that with Andromeda Galaxy? What do we get here? So again, it's really informed by sort of these, you know, one-off you know, data comparisons, and then that being sort of the justification and checks and balances that sort of build up that then helps them, you know, make their more global claim about like, this is successful, you know, within simulations, de-idealizing such that we can have the stellar stuff back in.
Thank you.
Thank you very much. Is there any question? We still have a little bit of time. We still have a few minutes.
If there aren't any questions, I do have an answer to John's question about gravitational lensing.
That's your opportunity. Go for it. John is gone. However,
Oh.
I mean, he's gone from the screen. So
Oh.
Nanda is among the attendees.
Oh, but he's still here. So
Yeah, go ahead.
So the really, again, cool thing about these galaxies is they're really, really small. And so they're like really hard to find. It's probably why we haven't found a bunch. We're working with like a new citizen scientist who's like combing through like tons of catalogs, and they're just like so tiny, like AI cannot be trained to look for these things. But because they're so small, and because of the frequency in where they're occurring in the universe, we haven't gotten lucky enough yet to spot one that has some gravitational lensing going on. But it could happen. So that's like a whole different like probability of these types of things actually occurring instance, but they're just super, super small, which is really cool.
John has joined us back. Here we are.
I don't want to preclude anyone else from jumping in. So, but okay, that's really interesting. So they're super, super small. So that raises two questions. One, why are they so damn small, right? That suggests something interesting in the gravitational physics. And two, if they're so small, do we have does that mean we can start to calculate the chance of a collision that will produce a ring? Because it's pretty important that that number's got to come out to be, you know, to be plausible. I take it these are all things you guys are thinking about, right?
We're trying, yeah. When pandemic and people power permit, yeah. So, I mean, part of the problem is they're so small, and there's no AI to actually like look for them. So part of what we've been doing is using citizen science folk, either like Galaxy Zoo or like literally just excited individual amateur or like they're not quite so amateur, but like astronomers are retired folks like just combing through galaxies looking for these for us. And so we're starting to get, you know, more and more possible candidates of these isolated rings, and using that as sort of like a springboard to try and figure out like just how many there are. But also if they're this small, you know, they have to be running into dark matter that's also like just so small. And the thing about a lot of these ring galaxies is if they just run into other, like it's like normal galaxy collisions, like if you don't have just the right size, they just get blown away or just like plowed over, or just incorporated into each other. And so those can just look weird anyway, but getting more numbers on those is something we're trying to do.
Can I ask another question? Or
Go for it, John.
So this is a wonderful opportunity for us to think about a new way of doing philosophy of science. I'm switching gears here. So you're, as it were, an embedded philosopher. I'm trying to figure out, how do you interact with a bunch of scientists? My feeling with those sorts of interactions is that very often they're expecting us to produce this profound nugget of wisdom. We say, trust in the wooden walls, and they say, ah, yes, that's it. Now we've solved our problem. And of course, we aren't like the Oracle of Delphi. We don't have the profound thing. So how do you sense that I heard you talk about doing a lot of ordinary science, right? You say we did this and we did that. How's your philosophical insights getting incorporated into the project that they're working on?
Yeah, so one of the main things, this is sort of cheeky, but like I just ask obnoxious questions, or at least like, luckily my collaborators love these kinds of questions, but like it's, and they like, I mean, it's the kind of things that they say, I wish we had time to think about these kinds of questions. And so by having a philosopher hang around with them, they get asked these kinds of questions, which they really like. But it is just asking a lot of questions. And I think philosophers are trained in part of what we do to ask questions in very specific and targeted ways, and in a more plurality of ways than scientists might be when they're just trying to focus on, results, or like, even their own individual goals within their norms of doing astrophysics. Like at the end of the day, they need papers that have data and results. And, sometimes in some ways, like the flip side of that in our currency is like asking a bunch of questions that also result in papers, but it's sort of like in trade-off of rewards that they just don't get to ask questions as much, and we get to do more of that. But they really like it, and they like having that as like part of their collaboration, so that they get to do that. And I guess, I mean, that's not what I would have said was my most effective like quality of being a group member, but it's what they keep saying is like one of the things that they like the best. So.
Do you remember any question that you asked that triggered them, or is that getting a little too deep into the weeds?
Oh, I mean, the most obnoxious one I asked was when we switched codes that we use. So at one point we were using a code, and then we switched to another one. And as a philosopher, I had invested a fair bit of time understanding what was going on in the first code. And then they decided to change. And I was like, but I learned all that earlier code. Why are we changing it? But so I asked a bunch of questions about like why we were using this new code. What was the reasons? Partly because I was grumpy, but partly because I was like, they must have some reason why we're switching besides, I don't know, this code's down the block from us. And they did. It just took a while of me asking those questions, and in some of those, it led to them being like, "Oh yeah, I guess that is a parameter that our code has that might become useful down the line. I hadn't thought of that."
Thanks, John. Thank you, Melissa. Is there any further question? We have 3 more minutes in case someone else has a last-minute question. 1, 2, 3. I guess the answer is no. Thank you very much for taking the time to talk to us today. It's been really a pleasure, and we hope that the attendees will join us for the next lunchtime talk, which will be on Tuesday next week with Nick Bird from CMU and Stevens Institute of Technology. Thank you very much.
Thank you all.
Absolutely. Have a good day.